Welcome, Math 13 students. I have our office hour lecture for section 11.2, contingency tables. So I'll remind people that we've actually already taken a look at contingency tables already, and you'll recognize them once you see them. Basically, a contingency table is a table of frequency counts for two differently distinct variables. There is a row variable and a column variable. This looks just like the stuff in chapter 4, specifically 4.2. You'll remember material that looks somewhat like this. We had rows, we had columns. Usually we had to add them up and find a probability. You can have lots of rows and lots of columns. There's really no limit on the size here. Let me give you an example of what I'm talking about. This is one I pulled from your homework. Here we have a sample where people were asked about their texting while driving habits and their seatbelt use habits. People were asked if they texted while driving, yes or no. And people were asked if they were irregular in their seatbelt use, yes or no. So this is what we mean by a contingency table. Two variables, one of them here, one of them here, and then frequency counts for those particular outcomes or categories. What we do here in section 11.2 is we test for independence. That means we test a null hypothesis that the row and column variables are independent. What do we mean by independent? It means that there is no real link between the row and the column variables. And the null and the alternative hypothesis are pretty straightforward. The null, row and column variables are independent. The alternative is that they are dependent or linked in some way. For example, let me bring that previous example back. One might think that risky behavior is risky behavior, and if you are likely to be irregular in your seatbelt use, you are also likely to be a texter while driving. That's really what this is about, if there is some sort of link between row and column variables. So as I say, the null hypothesis is that they are independent. There is no link. Knowing something about one says nothing about the other variable. The alternative hypothesis postulates a link. There are requirements, as there are for every test of hypothesis. You must be this tall to ride this ride. The requirements here, well, we need a random sample. We need frequency counts in a two-way table. If the data don't have that, then we can't use these techniques. And finally, we need an expected value of at least 5 for each of the cells or entries into the table, each of those categories. Those are the requirements. We're going to assume for the most part that they're met when we go through our tests. I do have some notation to share. Some of it we've seen before, some of it's a little new. O will stand for our observed frequencies. Those are the values that we're going to see in our contingency table. E will stand for the expected frequencies. Those would be the frequencies we would expect, assuming independence. Little r is going to mean the number of rows, and little c will give us the number of columns. I will note that we use a chi-square distribution, again, just like in the goodness of fit test. We even have exactly the same test statistic. The degrees of freedom for our test, though, is a little bit different here. It's the number of rows minus 1 times the number of columns minus 1. Now, let me talk a little bit about the expected frequencies. That enables me to get into the real meat of this particular topic, what we need to do our calculations. The expected frequency for each of the categories or cells, if you will, row total times column total divided by grand total. And we'll take a look at that, then I'll show you how we can find them nice and easily with our calculator. we have a dedicated tool. And that dedicated tool is called the chi-square test. And we use the p-value approach. So again, there's really nothing new there. Once we get the p-value, we compare it to alpha, and then we make a determination on the outcome. Here's what is different. We have to use what is called a matrix for our data entry. A matrix is a mathematical object of some import. It has a definition. The definition of a matrix is an array of numbers. I know that definition really doesn't clarify things. Let me give you some examples here. Let's consider a two-way frequency table here. We went out, we asked a group of people, we asked them their gender, and then we asked them if they voted or did not vote in the most recent presidential election. And we are going to test at some point that gender and voting are independent. There's no real link between if you're male or female and if you vote or don't vote. The alternative is that they are dependent and there's some sort of link. Now, this is our data here, and we take that data and we place it into what we call a matrix. A matrix has special notation. We have little square brackets on the outside, and in the middle, we've got the data arranged just as we see it in the table. We have a name. I called this matrix A, and it is the matrix of the observed values for this particular data set. So here's some more detail on matrix material. The class isn't about matrices, but you will be required to manipulate them to some extent. Now, a little bit about the matrix. Every matrix has a size. And the size is kind of like dimensions in a room or dimensions for a rug. They are always given row first, column second. That's the mathematical definition. Software and whatnot sometimes can mess around with that, but the matrix on the previous screen, that matrix A, is a 2 by 2 matrix because it's got 2 rows and 2 columns. Now, the numbers inside the matrix are called entries, and there are essentially coordinates to help us find each entry. For example, the number 21, the very first entry in the table, it's in the first row and in the first column. So it's A11 for the first row, first column, and that's my number 21. First row, second column is 16, and so on and so forth. Second row first, 33, and second row second, 10. So you can see that it enables us to locate and identify each and every number in a matrix in a very unambiguous fashion. Now let me talk a little bit about the chi-square distribution that we use to conduct these tests. This is a right tail only test. Right tail only. That makes things quite a bit easier. I don't have to make that determination. And basically, when my chi-square test statistic is large, we will reject the null hypothesis. That's when that test statistic falls in the rejection region north, if you will, of a critical value. Remember, this is not the T or the Z distribution. This is the chi-square. It only exists in the first quadrant. When that test statistic is small, we fail to reject the null hypothesis, and it would land somewhere in that general region. Here, reject. Here, fail to reject. Very much in keeping with what we've done before. Now, of all the tests we do this semester, this is truly, I believe, the easiest of the tests that we do. The biggest issue that we face is data entry. We've got to be able to input a data set in a matrix form into our calculator. But we have a matrix button, and we can take care of that quite easily. So let me come back to that data set about voting and not voting. Gender and voting are independent. That's my claim. There's my data set. My matrix is this guy right here. You've seen me carve it out on a previous screen. I also have row and column and grand totals in there also. And the reason, again, it's kind of glossed over it, the expected value is row total times column total divided by the grand total. And we're going to check one of them, then I'm going to show you how to find them very easily on your calculator. So we're going to test that claim. And let me go ahead and get started. So H naught, gender, vote are independent. The alternative, they are dependent. My initial claim is the null hypothesis, the claim of independence. All right, so let's go see how we deal with the matrix on our calculator. All right, and we have a dedicated matrix key. It's right over here on the left-hand side above the X inverse key. It's in blue, so second matrix brings up my matrix menu. We really only need one thing here, and that is that first matrix A. I can have any number of matrices in my calculator. I can do a whole bunch of very cool math. It's called linear algebra, but we don't need that. What we really need to do is to be able to edit our matrices. So matrix A will be my observed matrix. I'll hit enter. And the first thing I notice for the matrix I have is I have a 2-row and 3-column matrix, but I need a 2-row and 2-column matrix. I can easily adjust the size 2 by 2 and watch my matrix change. There we go. Now I can type in the 21, the 16. It does rows by rows, 33, and 10. So now I've got my matrix in there. And really, that's the biggest part of it. At that point, I can go directly to my chi-square test right there, right above the good fit test. The observed matrix is in matrix A. The expected matrix is in matrix B. I haven't said anything about B, and the cool thing is my calculator will deal with that all by its lonesome. So I can go ahead and hit calculate. Notice I've got a degree of freedom of 1. I'll talk about that in a moment. And I've got a p-value of 0.0570. Let me stop my sharing. So p equals 0.0570. I'm going to compare that to my level of significance. I didn't state one, but I'll use 0.05. And we're just a bit bigger than that level of significance. So we will fail to reject the null hypothesis. So at alpha equals 5%, data support independence for gender and voting. And that's your basic test of independence. One, two, three, four, five. And that really truly is the case for this material. As I say, it's one of the easiest tests we do. Now, I want to go ahead and do one other thing before I run through one more example. I want to talk a little bit about finding expected values. So for each entry, I need row total times column total divided by the grand total. And we had, let's see, 21, 16, with a total of 37. We had 33 and 10 for a total of 43. That was my matrix. Those were the row totals. Column totals were 54 and 26. The grand total was 80. All right, so for example, my expected value for the first entry would be 54 times 37 divided by 80. For the next one, it'd be 26 times 37 divided by 80. Then it would be 43 times 54 divided by 80. And then for the last one, 43 times 26 all over 80. The calculations are not hard to make, but they are tedious. Let me just make one of them. So if I just calculate the very first one, that is literally 54 times 37 divided by 80. 24.975. All right. Now, let me go ahead and show you one other issue on your calculator. And I can run through the keystrokes again also. So all right, so there's that expected value. If I jump back over to the matrix editor and I take a look at matrix B, well, that looks impressive. But if I hit enter one more time, I get the matrix of expected value. My calculator goes out and it does that just automatically in the course of working this hypothesis test. So I could use those formulas, or I could just ask matrix B. All right, let me take a look at one more example, and then we'll be done. This is number 16 from your problem set. And we have a helmet color for motorcycle accidents. We have a control group, no accident. We have a group that did have an accident. So no accident group. We have color of helmet. We have black, we have white, we have yellow or orange, and we have red, and we have blue. And we have 491, 377, 31, 170, 55, 213, 112, 8, 70, and 26. Claim, injury, helmet color are independent. So there's my data. This is number 16 in your problem set. I will note that I have a 2-row by 1, 2, 3, 4, 5 column. So my matrix of observed variables is 2 rows by 5 columns. All right. So let me go ahead and run through that test. H naught. Injury color are independent. The alternative, they are dependent. So all I need to do is to find my p-value, compare it to my alpha. Oh, what is my alpha here? I'll use a 5% alpha. Why not? So back over to matrix. I need to edit matrix A. I use matrix A for every problem. I have 2 rows and 5 columns. Oh dear. Let me try that again. All right. 2 rows. Come on, man. 2 rows and 5 columns. There we go. So now I can type in my data. 491, 377, 31, 170, 55, and for the injured, 213, 112, 8, 70, and 26. All right, so my data is in there, literally right to chi-square test. I don't have to add or change anything. And there we go, 0.0409. And let me stop my sharing. So 0.0409, 0.05. My p-value is less than my alpha, so I will reject H naught, and I can say at alpha equals 5%. Data do not support independence between injury and helmet color. What does that really mean? Color matters. Some colors appear to be better at standing out than other colors, which might mean fewer accidents. So there we go. It is truly the easiest test we do all semester. There's only one other issue we might have with this data. Some of those numbers were a little low. So I want to check my expected values for that matrix. Now, some of you might say, oh, but Chris, it was a 2x2 matrix from the previous problem. Well, I will note that matrix B is now a 2x5 matrix and contains those expected values. Notice I have a lot of decimals. I can't even see my entire matrix. But if I look at all the values, I can see none of them are less than 5. So my expected requirement is fulfilled. and my results should be valid. So there we go. That's your section 11.2 contingency tables and your test for independence. This one actually gets used quite a bit in the land of statistics. It's a very interesting and honestly quite a straightforward and easy test to run. So go ahead, take a look at that material. There are more videos available in our Canvas course shell. Send me any emails you might want to regarding questions and I'll get back to you. Thank you and goodbye.